ഓക്കെ സാറേ. ഓക്കെ സാർ. നമുക്ക് തുടങ്ങാം എന്നാല്. ഓക്കെ സാർ. So, a very good afternoon to all of you. First of all, let me introduce myself. I am Sandhya from the Department of Physics, Mahatma Gandhi College, Irpi, Kannur district. It's my privilege to be a part of this webinar series, being organized to pay homage to a great Professor Aruldhas sir, who was a real mentor during his period. So, my official duty here is to welcome the gathering. For any event to become successful, there has to be a proper planning, and that planning requires a lot of effort. And I see that we have a very efficient organizing committee. We are just host colleges, and the effort was mainly made by all the organizing committee members. So, first of all, I welcome each and every member of the organizing committee to this seminar series. And as we are all aware of, today we have Dr. VP Sudeep Kumar from BSNL Trivandrum. He is Assistant General Manager, who is going to deliver his talk on ultra high capacity fiber optic communication. And I am a bit proud to invite him because he is my classmate. So, with immense pleasure, I welcome Dr. VP Sudeep Kumar to this gathering.
Thank you. Thank you.
Okay, and for any program to be successful, it is decided by the participants, mainly the student community. I welcome each and every participant to this webinar series. And I have a small request for all students because the student team consists of the selected students from various colleges all over Kerala. So I request them to grab even very little information they could from this seminar and pass it to their friends at their respective colleges. Only then many students can be benefited out of this webinar. So welcome all students and participants to this webinar series. I also welcome my colleagues Sapna P and Ashok Jairam to this webinar. I also take this opportunity to express my sincere gratitude to my principal, Dr. Ajita V, who extended full support and granted me permission to host this event. With these few words, and one more thing, many of our batchmates from the University of Kerala has shown their interest to attend this webinar, and that's also very good. I welcome all those members, and a special welcome to our dear Unikrishnan sir, which indeed made this event colorful. With these few words, I welcome Sibisa, Head of the Department of Physics, University of Kerala, Trivandrum, to say a few words about this event. Sibisa, please.
Okay, thank you, thank you. Hello. Okay, okay, okay. So can I start now? Okay. Hearty welcome to one and all, respected CB sir, respected Undikrishna sir, other dignitaries, my dear friend Sandhya, and all other faculties of university students all. Actually, I am happy to be a part of this webinar series because Dr. G. Aruldhas was my teacher and also he was my MPhil guide, and I am very happy today because I can at least remember remember his teaching style because he was a great man. When we ask questions, he is ready to answer in a very simple, light, transparent way. Okay, and now I am directly logging into our topic. The topic of the day is ultra high capacity fiber communication. So I will go slide by slide. So the agenda today. First is we will have a small basic introduction. Then we will study multi-wavelength fiber communication. Then optical amplifiers, erbium doped fiber amplifier and Raman, elasto-optic networks, trends in optical fibers, submarine cable communication, and we have some conclusion questions, etc. Actually, for the first 10 to 10 minutes, I will take for some introduction so that all will be the same level. I will try to do that. Some basic things will be covered, but you have to bear with me. Usually in seminar and webinar or anywhere, the questions will be at the last, but we will start from some questions. Okay. So what is meant by bandwidth? Why infrared light is used in optical fibers? Why the bandwidth is so high in optical communication? You all are the physics lovers, and actually the fiber optic communication is for the physics and the physics lovers, physics teachers, physics research, physics students. But it is some way it is trapped and snapped by many of the engineering wing also. But physics is the core. Anyway, what is mean by bandwidth? I will tell you an analogy. For example, you are in a class and the teacher is the source and the students are the receivers and the media is air. For example, you assume that the teacher is telling 10 points per minute and all students are hearing, and for example 10 points per minute is the bandwidth of the teacher, because bandwidth means when I ask this question, what is bandwidth in the students will tell it is the frequency range, like that. Actually it is right, but bandwidth nowadays we can tell in digital communication as the number of informations per second, how much data per second, how much bits per second. Okay, back to the analogy. That is, the teacher is telling, let it be 10 points per minute, ppm, a unit. Okay, so not parts per million, it is points per minute. So 10 points per minute is the bandwidth of the teacher. That is, I call source bandwidth. Now, the students all can hear the information through air. So air is supporting, the media is supporting 10 points per minute, and the students hear 10 points per minute. And I presume that the students are taking only 5 points per minute because they can understand, they can detect, they can trace it out only 5 points per minute. So the source bandwidth is 10 points per minute, the media bandwidth is 10 points per minute, and the last receiver bandwidth is only 5 points per minute. Of this, only 5 points per minute is the throughput or the actual output, and we call this as the system bandwidth. That is, minimum of the source bandwidth, media bandwidth, or receiver bandwidth will be the actual bandwidth that effective, or it is called as effective bandwidth, throughput, system bandwidth, bandwidth of the system, like that. Now, you assume that situation, that is, if the teacher is teaching the students in an auditorium, that is, the distance is huge. If a teacher is telling 10 points per minute, the bandwidth is correct, no change to the bandwidth of the source. But the media, the length increases, the bandwidth decreases because of the loss. Okay. Now the student was able to detect 5 out of 10, but now only 3 or 5 is reaching, so the student bandwidth also accordingly decrease. So the actual bandwidth is now, for example, the media bandwidth is 3 ppm. So I am telling that is the bandwidth of the whole system is now only 3 points per minute. Now we assume the class is an afternoon class. The bandwidth of the receiver will be not 0, but it is nearly 1. Is it? Maybe. So afternoon class means the detectors are...
One minute. Are you putting the slide? Slide is not clear. That is why. Everybody is seeing the slides.
Okay, sir. I will make it.
സാറേ അത് പിൻ ചെയ്താൽ മതി സാറേ, പ്രസന്റേഷൻ ആ സ്ക്രീൻ പിൻ ചെയ്താൽ കാണാൻ പറ്റും സാറേ.
Okay. Now clear. Okay, sir. Sunday, is it okay?
ഇപ്പൊ കാണുന്നുണ്ട്.
Okay. So now, okay, sir. That is now if the so what is the actual bandwidth is minimum of these 3. Now, in olden days, the source was giving, or source has the capacity to give any bandwidth, but the media was at that time was copper, then it is changed to a coaxial cable, then microwave, then satellite, everything. But when the media became fiber, there is no question of bandwidth deterioration, or what we call, if the source gives 10 ppm, the media also support 10 ppm. That is, the source, when it became media, when the media became the fiber is asking to the source that you give as you can, I am ready to give the destination. Or the bandwidth of the fiber is infinite, not infinite, it is very high. Or the fiber optic technology has actually revolutionized the bandwidth with unlimited provision of bandwidth. Now again, our question remains, why the infrared rate? I will come to infrared. Then why the bandwidth is so high in optical communication? That is, a golden rule is there. That is Shannon's theorem, which is considered as the golden rule in communication. That is, C, the channel capacity, how much data can be carried, is equal to the bandwidth of the carrier multiplied with signal to noise ratio. Means, I will tell in a simple way, not actually right, but can be. That is, if the carrier used for transferring the data or the carrying the data is in kilohertz range, we can have to carry kbps of data. If it is a megahertz range, we can have mbps of data. And if it is a gigahertz range, it can carry gbps of data. And in the case of fiber optic communication, the infrared light is a terahertz wave, so we can have tbps of data. In a simple way, we can explain like this. So it is not due to total internal reflection, or it is not due to the light alone. It is infrared light, which is a terahertz wave, and is contributing this huge bandwidth to the fiber optic communication. Because all electromagnetic waves undergoes total internal reflection. Then you may ask me why this infrared alone is used in communication, because even visible light is having higher frequency, ultraviolet, X-rays. Now the answer is, in the case of fiber optics, fiber is made of glass, glass is made of silica, silica is silicon dioxide molecules, and these silicon dioxide molecules will not absorb infrared, lightly speaking, or it will not go any resonance absorption. So that is the reason why fiber optic communication, the infrared light is used for as laser for communication. So two questions I answered. Why the bandwidth is high? It is due to the, as per the Shannon's theorem, bandwidth is directly proportional to frequency, and also the loss, that is C is equal to B log 2 to the base 1 plus S by N, signal to noise ratio. For example, in communication, if 1 milliwatt is the signal, in the case of fiber optic communication, if 1 milliwatt is the signal, the noise is nearly nanowatt. But in other communication, if 1 milliwatt is the signal, then the noise can be even 0.01 milliwatt, like that. So the purity or the quality of the signal is very high in the case of fiber optic communication. That is the log 2 to the base 1 plus S by N, which is multiplied with the high bandwidth, that is a terahertz wave, that is infrared, is contributing the huge bandwidth to the fiber optic communication. So now I answered what is meant by bandwidth, why infrared light is used in communication, why bandwidth is so high in fiber optic communication. You see, once upon a time, we browsed BPS, then KBPS, then MBPS, GBPS, GPPS. Now we are living in a data tsunami era, or terabit era, or a terabit domain, where the data transfer, 1 TPPS is nearly equal to 60 volumes of 60 encyclopedias per second. So that is the huge bandwidth provisioning that can be done through fiber optics. Now 2020 is a terabit domain. Tomorrow it will be petabit. Actually, the research development are on with the petabit domain, exabit. Peta means 10 to the power of 15, exabit is 10 raised to 18, zetabit is 10 raised to 21, and yotabit is in 2030. People will be browsing in yotabits per second. YBPS technologies will come. That is the prediction of the optical Moore's law. Now, again, one point I missed, that is regarding this how this happens. Actually, it is a very simple communication system compared to any other communication system. For example, if one person is telling hi, that is an analog signal, and when this analog signal is converted into digital signals, that is 101010, for example, hi 101010, at this point there will be, at the source point there will be a laser, which is an infrared laser, and which is going 1 is equal to on, 0 is equal to off, 1 is equal to on, 0 is equal to off. So how many times it is going on and off is the bandwidth of the source, or the bandwidth of the bandwidth of the laser. You may wonder, that is the source bandwidth may go up to GPPS. That is, a laser can go on and off with distinguishability up to 10 to the power of 9 times in a second. So that is the advantage of these lasers, that is semiconductor lasers, when it is used at the source. And within the fiber, in fiber I told it can go up to terahertz. How it will be, that I will explain. Then last point is actually converting the optical signal to electrical signal by a pin or a PN diode or a photodiode. That is, 3 technologies converge in fiber optic communication. One is electro-optics, then pure optics, then optoelectronics. Understood? That is, 1-0 becomes on-off. On-off is going as light, and this on-off is detected as electrical. That is, the bandwidth of the fiber means how many on and off can carry per second. How many light, Malayalathi parnal, how many light undu light illa per second is the bandwidth of the fiber. Okay, agree. Now you see the source. You can see here is the semiconductor laser. 1 is coming, light is going. 0 is coming, now light is going. You may wonder how this is happening. That is the power of the optical laser. That is, the bandwidth is very, very high. And you can give 1 0 1 0 1 0. The light will go on and off, on and off, on and off. You may be knowing how the fiber is made of. Fiber is a pure silica with a core within only 9 micrometer and cladding nearly 125 micrometer. And it is in commercial use, it is coming with 400 micrometers of primary coating, then a secondary layer of coating. Actually, 125 micrometer is 1/10 of a millimeter, 0.125 millimeter. So very, very small. These fiber is carrying terabit of traffic. And I told you at the beginning that infrared is having the lowest absorption in silica. And when you consider the evolution of optical fiber communication, the first window, that is the minimum point, was this 850 nanometer, which is called as the first window in optical communication. Nothing. The laser used was 850 nanometer laser. But research, development evolved, and another second window came at 1310 nanometer. Another laser developed. That was in 90s. And the third generation was 1550 nanometer. This is the actual window, what we call C-band in fiber optic communication. So these are called the windows in communication, where the low. This peak is water peak. That is why this region we can't use 1480, that range. That cannot be used. And now low water peak fibers are also available. And this is the region. That is, if you see the telecommunication networks or fiber optic networks all over the globe, you can see that only this almost all the wavelength used for this communication is in the range of 1550, 1530 to 1565. This is the region. That is DWDM range. So rise and rise of optical fibers, you see, starting from 1960. At 1960, invention of laser by Shallow and Towns, that is semiconductor lasers. Then 1965, the optical fiber by Charles Cave and Hackham. And this is the invention. He is called the father of fiber optics. Dr. Q.N. Cave is called the father of fiber optics. And he discovered, actually, he has made the purity of the silica to a higher level so that the loss has been decreased. That is, when it was discovered, it is 20 dB per kilometer, which means that 1/100 in a, no, 20 dB per meter, that is 1/100 in a meter. 100, for example, 1 milliwatt becomes 1/100. But now the technology allows that is less than 0.2 dB per kilometer. That is 1 milliwatt. If you pump from here at Koilan, you will get as 1/100. That is, the loss has decreased drastically. And this Q.N. Cavo, one important thing is he is considered as the father of fiber optics, and he discovered the fiber in 1965. And he got Nobel Prize in 2009 for the discovery in 1965, which itself tells the story of fiber. For the importance of fiber optics. At that time, when he has presented the paper in many conferences, people ridiculed him by telling that, what the man is telling. Is it possible to lie? What? Nothing. Because at that time, the microwave was the uncrowned king in communication. But that has been snatched because of the discovery of 1965 by Charles Cave, coupled with the invention of laser. Without laser, fiber is nothing. Okay. And in 1970, optical fiber were made actually by Maurer and was installed by British Telecom in 1972-73. 1980, again, what happened? Optical amplification, that we will discuss. In 1990, optical links was used for the internet, that is WWW. That was a turning point, that is a start of the data tsunami. That is till that time, the people were using this for voice communication and all. But when it was used for World Wide Web Internet, the data-hungry applications were demanding the bandwidth. Data traffic exceeded that of the voice in 2000. 2010, the gigabit communication system started, and we are in 2020, and we are now marching towards terabit era, or the terabit communication system. Again, the fiber optic communication system is a very simple system. It is going by on and off. And you will ask, is it everything on and off? No, that I will tell. But up to 1 Gbps or up to 10 Gbps, we can go with on and off modulation, or what we call NRZ modulation, or on-off keying. That is, laser is internally modulated, and this is type of internal modulation. You can also modulate the laser externally also. That is, after the light comes, a continuous wave laser, and in that light we can change the quadrature, we can change the phase, we can change the amplitude. That is called external modulation. Just like if you are making a torchlight on and keeping your finger, keeping your palm like this, on, off, like that, you can make it. That is called external modulation. Now, we can, using this technology, we can go up to 10 Gbps per second. That is not actually correct, but correct. That is, this is an on, and this is the, after 100 kilometers, it is like this. So it is 1 bits in a second you take, and here also it is 1 bit in a second, but it is distinguishable, though it is bulky, called by means of dispersion. It is just like pulse is spreading. And if in this, if I am increasing the bandwidth 3 times, that is 3 bits per second, what happens here? You can see all are bulky, no problem, but it is, the detector is unable to distinguish between the events. This just like we are unable to distinguish what is it. Now the detector is looking for one off and on, but all are on. So this is the spreading of signal. When it is at the start, it will be okay. Then it is spreading, again spreading, last it merging. The detector is just looking, nothing. They cannot detect between events. So, sir, you told me, you may ask, that it can go up to terabits per second. Now you are telling only 10 Gbps, only this Gbps domain. No, that is when there is a risk. For example, there is a bottleneck. The researchers will always find other methodologies to handle bottleneck the problem, because the demand is huge. So there should be something to be given to satisfy the bandwidth hungry applications. So you see, you can see the services, triple services, VoIP services, 3G services, MPLS circuits, VPN circuit, all demanding bandwidth hungry applications. And it is asking the fiber optic man to give the bandwidth. You are telling that is dispersion is, because of dispersion, the bandwidth cannot be given more than 10 Gbps. Yes, that is called electronic time division multiplexing. There is a limitation, but there are many methods by which we can increase the bandwidth. The one simple and the easiest method is, for example, Trivandrum Kollam, it is working with 1 Gbps, and the Kollam man is asking, I want 10 Gbps, then you can lay 10 fibers. But it is not worth, it is not a cost effective, it is not a reliable system, it is not a quality system. So please overrule the FDM technology. Then higher bitrate using the fast electronics, that was up to 10 Gbps only, and the remedy or the best cost effective fit solution is WDM, or wavelength division multiplexing. So the last, WDM. So we are changing from single wavelength communication to multi wavelength communication. For example, this clearly tells how a WDM works. This is a fiber between Trivandrum and Kollam. You can see this is a simple fiber, Trivandrum, Kollam. And previously there was only one wavelength, that it may be 1550 nanometer, may be going through the fiber by total general reflection. But now all are taken together. That is 1550, 51, 52, 53, 54, n number of wavelength you can take. You can couple it or multiplex it. That is optical multiplexing. Then launch it into the fiber. It is going through the fiber and it is retrieved back. The spacing between these wavelength, now it is 0.01 nanometer is available between the wavelength spacing of the laser. For example, 1550, 1550.01. That is ultra dense wavelength division multiplexing. Actually, this is the way it is going. Now, this wavelength division multiplexing is also of three types. One is called bidirectional wavelength division multiplexing. That is, bidirectional wavelength division multiplexing means the, for example, one transmitter and other is a receiver, and if there is a single fiber available, then if the laser is going on and off here, it is going in 1310 nanometer to the destination, and from there another wavelength, the same fiber is going. That is both way. That is called bidirectional wavelength division multiplexing. That is 1310 from the transmitter to the receiver and 1480 from the receiver to the transmitter. Bidirectional wavelength division multiplexing. Then CWDM. Actually, this is the technology by which the people are using fiber to the home technology. That is BWDM, bidirectional wavelength. Single fiber will act as a trans and the receive. Then technology is coarse wavelength division multiplexing. Coarse in the sense that if you see the laser 1550 and 1552, 1554 like that, the cost is very high. But if you take a fiber 1550, then 1520, 1570, the 20 nanometer difference is there. It is not a costly at all. So what is the for example, if one need a metro network that is within 20 kilometers, a small network is to be created, he can go for coarse wavelength division multiplexing. And ITUT is the International Telecommunication Union. This is the standardization body. For example, any company can come up with, they can make a CWDM network, but the wavelength should be as per the standard by the International Telecommunication Union, then only it will become interoperable. Then DWDM is the dense wavelength division multiplexing. For example, 1530 to 1565, if you take, you can have 16 lambda, 32 lambda, 128 lambda like that. If you are telling 128 lambda, which means that 1 Gbps or 10 Gbps, which was running through a single wavelength, is now multiplied with 128. That is why the DWDM technology is also called virtual fiber technology. That is, it is virtual, but it is equal to one fiber. The wavelength is the carrier. That is the beauty of the technology. Now, self-explanatory, that is lambda 1, lambda 2, lambda 3, lambda 32. It is 32 lambda system at the transmitter. It is optically multiplexed. Why I am telling multiplex and optically multiplex means there is no conversion from the optical to electrical to optical, OEO conversion. The light is coming, light is going. Light is multiplexed. Just like this. For example, first light, that is 1551 multiplexed, 1552, 1554, and 1556. You can see the wavelengths are going. Each wavelength is carrying 10 Gbps. So 10 Gbps system with a single wavelength becomes 40 Gbps. And if it was a 40 Gbps in a wavelength, then it becomes 160 Gbps. So the technology or the fiber, the same fiber which was laid 20 years back, can be absolutely useful for increasing the data traffic from Gbps, 100 Gbps, if it is 100 lambda, if it is 1000 lambda, like that. But there is limitation that I will come. It is to explain our prism is an optical multiplexer. That is, it is a 7 lambda coupler or a 7 lambda multiplexer. White, indigo, blue, green, yellow, orange, red, all are combined together in a fiber without converting to, that is, it is a single light wave which is going through the fiber. So all the 7 wavelengths are now going as a single wavelength through the single mode optical fiber, and it is reaching there and it will be retrieved back. Another view, 155, 152, 5354, 1 nanometer is a separation, and all are merged together and it is going to the fiber. For example, if you take a Trivandrum coilon link and if you cut a terminal and if you connect to a spectrum analyzer, you will see these spectrum. For example, the lambda 1 corresponding to the link from Nayatinkara to coilon, lambda 2 may be from Kattakada to coilon, lambda 3 may be from Nedumangadi to coilon, another may be from Karivattam to coilon. That is, each wavelength are carrying information just like a fiber. This is at the egress point, that is where the bandwidth is decoupled back, or the wavelength are demultiplexed. So the beauty of the technology, if you take an electrical multiplexer, you can see number of ICs, transistors, and other equipments in boards, so that these process can be done. But in the case of fiber optics, it is an optical domain. What is the difference between optical domain and electrical domain? For example, what happened in 1947? You may think India got independence. Yes, but 1947, William Shockley discovered the transistors. Actually, till that time, it was electromagnetic exchanges, electromagnetic technologies, electrical technologies. Okay. So after the advent of these transistors, the situation changed. The technology shifted from electrical to electronics. Okay. Or in my language, it is from kbps changes to mbps. Okay. 1960-65, the semiconductor lasers and the optical fiber changed the technology from megabits to gigabits, or optoelectronics or electro-optics happened. And now what is happening? It is not optoelectronics, electro-optics, pure optics. That is optical domain. Optical is very fast. Optical domain. Optical domain means there is no no delay at all. There is no bandwidth limitations. It is high-speed networks or terabit networks or TBPS networks. So here there is no conversion to electrical or electronics. Purely it is optics. So this is the demultiplication. For example, Trivandrum, the link reaches coilon. It is 1, 2, 3, 4, and it is given back in the optical domain. So there is no loss at all. And these are the dense wavelength division trends is towards smaller spacing, which means that the spacing should be small, so that we can accommodate more number of wavelength each with each data. Point for 0.8, 1.6 are the standard commercial applications, and now we are getting 0.2 nanometer, even 0.1 nanometer, 12.5 gigahertz spacing. Research and development is for having 100 Gbps in a single wavelength. So this is another view which will be explaining very neatly how it works. For example, in your office, there are 3 computers. Each are connected to an electrical multiplexer through 1 Gbps, 1 Gbps, 1 Gbps link. So the output of this electrical multiplexer is 3 Gbps, which is given to a semiconductor laser, which is giving, for example, 1550 nanometer. So 1 is equal to on, 0 is equal to off, 1 on, like that. So these are pumped into an optical multiplexer. So this is a simple 3 lambda system. So the whole bandwidth is 9 Gbps, simple. And it is going to a single fiber, reaches the destination, demultiplexed back, and it is now going to different computers. So this is the way you can think. Now the technology has allowed up to 1046 lambda systems. That is 1046 lambda from 1310 nanometer to 1620 nanometer. That is, they are now flattening the complete bandwidth and utilizing in a single fiber. This is I already explained, this bidirectional wavelength division multiplexing, that is the wavelength from the transmitter to the receiver at 1490 nanometer and from the transmitters to the receiver at 1310 nanometer. This is the fiber to the home or bidirectional wavelength division multiplexing. Okay. Coarse wavelength division multiplexing. Also, I told you that it is a cost-effective technology. That is, if you want to have a metro network, a LAN or a WAN within a Prima, for example, Trivandrum, I want to make a metro area network, then I can make use of this technology so that the cost effectiveness and also that is enough to have the quality. Then another technology is optical anti-rot multiplexer. Actually, it is the equipment which is associated with DWDM, dense wavelength division multiplexing. You can see, you assume that a link is from Trivandrum to Ernakulam. Okay, and in that link there are 4 wavelengths are passing through the fiber. 4 wavelengths, that is 4 lambda system. At Alleppey, I want to drop 1 wavelength or 2 wavelength. It is possible. That is called OADM, optical add drop multiplexer. Previously we have it, but it is an optical add drop multiplexer with conversion from optical to electrical, then retiming, reshaping, regeneration, then converting to optical. But this is pure optics. That is no conversion. You, for example, 1, 2, 3, 4, you down, that is 2 and 3, 1550 and 1551. Just like a bus is going and the teacher is telling to the students that Raman and Krishnan, you get down. And then another 2 people, that is Levan and Kushan, enter. That is the technology by which optical add drop multiplexers are available, and these are called triple O networks. That is, there is no electrical involved. Now, optical cross connect. In the previous case, you may be knowing that is only 1 fiber is coming and going. But in this case, you see, the number of fibers are coming and the number of fibers are going out, and each fiber is having different DWDM system. And the advantage with optical cross connect is, we can tell, for example, from the first fiber, lambda 1, lambda 7, and lambda 8, you go to the third fiber as lambda 7 and lambda 8 and continue. And lambda 2 and lambda 3 you get up. And instead of that, another lambda 2. So enormous flexibility, no passcode plugging in, nothing is required. You can just right click, you can make it, just drag it, it will go like that. So that is the beauty of the optical domain, which are, because if you convert something to electrical, for example, I am speaking in English, and if you know English, then no problem, because there is no choking. But you know Malayalam, I know English, then there must be an intermediary. He must convert this to translate. Sorry, he must translate this idea to him. Similarly, here electrical domain is now completely vacated and pure optics, triple O networks, only optics. The previous case, if you are thinking that in our electrical domain, NAND gate means on, off, 0. Here on, off, on, light undu, light illa, light undu. So the technology. But one of the difficulties that optical domain faces is the buffering, because it is very difficult to latch optics light. So now the hot topic is optical amplifiers. So I will go. Okay. Optical amplifier. Okay. Actually, I will go back to my old link, that is from Trivandrum to Koilon. At Artingel, the intermediate point, I want to amplify. Before 1997, 90s, 95, what is to be done is, the data or the traffic which is coming for the optical signals are converted into electrical, retiming, reshaping, regeneration, amplification, that is, amplifiers are to be used. Then it is to be converted into optical and go. But erbium doped fiber is a technology, very simplest technology by which we can amplify the optical domain itself. That is, for example, here you see the picture in which there is a coupler available, and there is a pump laser available, and this is the incoming. For example, incoming pulses 1550, for example, 1530 to 15658 wavelengths are incoming, and there is a pump laser by which it is passing through a fiber which is doped with a fiber. Sorry, erbium. Simple. So if you hear about an amplifier, you will think amplifier means there is an electrical circuit. Nothing. Here it is a symbol. If one input with a pump laser passing through a erbium doped fiber, what happens? This is the output. That is the technology I will tell you. Okay, actually, when we pass a pump laser that is 980 nanometer into a erbium doped fiber, the erbium doped fiber, erbium will go to the excited state, then go to the metastable state. And when it transfers from metastable state to the ground state, it emits 1550 nanometer. That is why erbium is chosen and doped. A rare earth doped fiber is made because this erbium has a meta to ground state transition in 1550 nanometer, 1530 to 1565. The incoming pulse train, our C band, that is also 1530 to 1568. That DWDM coming is also 1530 to 1565. Meta to ground state also 1530 to 1565. How this is made into metastable by this pump laser, that is 980 nanometer. If you impinge into the fiber erbium, which is doped with erbium, erbium ions will go to the excited state and then it will go to the metastable state. The incoming pulse is also of the 1550, so it causes a stimulated emission, the same principle of laser. And huge amplification takes place. This we measured at Karyavatam when we done this PhD and all. So, use of ETFA in an optical link. You see, erbium doped fiber from Trivandrum, Kollam. For example, the link length increases from 70 to 600 kilometers. For example, if you use 3 amplifiers in a link, for example, a link is 70 kilometers, and if you connect or if you insert 3 amplifiers, that is erbium doped fiber amplifiers, what happens? The link length changes to 600 kilometers. That is, this is called the booster amplifier. This is called the inline amplifier. This is called the pre-amplifier. Okay, all are ETFA. And if ETFA is not there and also DWDM was not there, the situation will be like this. You see, Trivandrum Bangalore link. No DWDM, no erbium doped fiber amplifiers. The situation, you see, 32 connectivities are required, then 64 fibers, transmission and reception. 7 not for 3 R, that is regenerators. And also, it is 7 not for regenerators. Now, when this is replaced with a optical amplifier and also a DWDM system, the situation is 2 fibers and also 5 optical amplifiers. You see how simplified the network. And ETFA and this is Raman only. That is, ETFA is an erbium doped fiber amplifier. That is, we have to use erbium doped, and it is, for example, we can amplify only from 1530 to 1565. But now the world is with Raman amplifiers. You all know non-linear Raman, inelastic scattering, Raman amplification due to the non-linearity. That is, here, what is non-linearity? You may be knowing. That is, when the refractive index is a function of wavelength, this is nothing. It is what we know. But when it becomes also a function of intensity of light, it is the non-linearity. In fiber optics, I will tell. For example, if I am passing 1550 nanometer at 1 milliwatt, I am getting as after 70 kilometer, I am getting as 1550 nanometer at 0.1 milliwatt. But if I am transferring 10 milliwatt or higher milliwatt 1550 nanometer, I am getting at the destination with some changes, a shift in wavelength, because it becomes an intensity function also. That is, it is a function N to I, you may be studied it, N2 into I, that is non-linear refractive index. Similarly, here in fiber optics, Raman amplifiers are used in many networks. For example, mainly in the undersea cables. What is the advantage here is, here it is a tunable amplifier. For example, if I want to amplify 1530 to 1565 nanometer, just 10 nanometer or 15 nanometer behind, I will use a pump so that it will shift or it will amplify the actual region. That you can study later. Anyway, it is a tunable amplifier, but the noise is higher. That is why it is not used in terrestrial networks. But nowadays people are using it. Japan is the pioneer in using this type of Raman amplification for undersea communication. So when we started, I told you 3 windows only. That is one 850 nanometer, 1310 nanometer, and 1550 nanometer. Now you see the wavelength windows are changing to bands, because now the people know the importance of bands. Instead of one wavelength, if we can. So O band, original band is there in from 1 to 6. All these are far infrared range. Okay, water peak, E band, then S band, 154. Actually, this is the band used by almost 90% of networks today in normal codes. That is 1530 to 1565, 35 nanometer C band, where 85 is a very fundamental amplifier, or it is a very nice. Then L band amplifiers, U band amplifiers. So all the optical band is now taken away by the fiber optics people or fiber optic communication people. So now in use. Now this is a peak 1480. I am not very versed on that, but you may be knowing that this is the 1480 nanometer of the H2O bending or some vibrations. You may be very familiar with that. And if this can be avoided, this is also a very nice band. But this is the band here. It is used for FTTH because it is a short distance, so water peak is not a problem, or water absorption to the infrared is not a problem at all. So this is the different types of research and development and trends in optical amplifiers. For example, tellurian Doppler fiber amplifiers, Raman plus fluoride, because you can couple different types of amplifiers. For example, 1530 to 1565, you can use YECFA. From 1310 to 15, you can use Raman, and another area you can use Presidium Doppler fiber amplifiers. So it is hybrid amplifiers you can have with him, so that when a 1046 lambda is impinged into the Raman block, for example, amplifier block, it will amplify its own defined area. Now, okay, now future elasto-optic networks. So in the case of DWDM, dense wavelength division multiplexing, you can see 1530, so 1530, then 1532. There is a 2 nanometer difference is there. Actually, it is a loss. Actually, it is not an efficient way of defining, because only static type of allocation. But if a customer is asking for 10 or 100 Gbps, we can give a big band. For example, 1530 to 1565. If a customer is asking for 1 Gbps, we will give a narrow band, again higher band, like that. That is called elastic wavelength division multiplexing. That is not fixed wavelength. It will go like this. You see, depending on the user case, we can have a big bandwidth, smaller bandwidth, very smaller bandwidth, like that. And also we can have different modulations of quadrature, phase shift keying, QPSK, 8 PSK, 32 PSK, 1024 PSK, like that. So if a customer is asking something, or so a connectivity is asked by an internet service provider or somebody, then we have to give, actually it is not implemented, it is on the verge, and it will be coming. That is bandwidth variable transponders, then modulation variable transponders. All things are coming, and which will contribute another addition to the bandwidth enhancement, and it will anti-bottleneck the bandwidth hungry applications. Actually, fiber gratings in optical communication. If you see the optical fiber communication systems, you can see that fiber gratings is the key element in all these. That is, in the fiber, there will be a core, you may be knowing. The refractive index of the core is modulated with the periodicity. This is the main element. This is used in many communication links. So you see, this periodicity, for example, if you are passing a broadband source, for example, 1530 to 0.6 nanometer to 1620 nanometer, the far infrared range. And it is passing through a fiber with a periodicity of lambda. For example, periodicity, if it is a micron, then it will act as a reflection grating. If it is in mm range, that is 0.7 mm like that, millimeter range, it will act as a transmission grating. You can see the output. For example, 1530 to 1565, if you are impinging, then you are getting 1530 alone as the reflection. All other will pass through. But here, one will be missing and all other will be passing. One is a transmission grating, another is a fiber grating, is a reflection grating. That is another beauty is you can tailor it. For example, which wavelength you want to decouple. For example, effective index of the core you can adjust. That is index of the core, and also the periodicity that is used by UV for example, exposing the fiber to the UV light so that photosensitivity changes and the refractive index accordingly, and you can tailor and you can make which wavelength you want to decouple from a continuous wave. So the wonder is you can use an International Telecommunication Union fiber grating filter. Then dispersion control can be. Then it is used in ETFA as a gain flattening filter. It is used in optical OIDM, and it is used in tunable filters, ETFA, and everywhere in the communication link. If you take it is a fiber grating, that is very, very important for a physics student, because he can explore without limitation to this optical domain and can have a better research methodologies, and you can have more research on this, because for my understanding is for about 20 to 40 years, there is no counter technology to replace the fiber optic communication. Then optical fibers. So you see the optical fiber, there are different types of fibers available. Nowadays, ribbon fibers are coming. Ribbon fiber means 12 fibers are same. What is the advantage is while you can splice it very easily. These are the standards. For example, if you want to make a fiber, then you have to support a standard. Then only you can market it globally. For example, ordinary fiber is G652, which means a 9 micrometer core, 125 micrometer cladding, 650 nanometer, 1.4658 is the core diameter, 1.465 is the cladding diameter. So everything is specified in this type of ITU standards, and you can make it so that you can tell. For example, if I want to procure a fiber, then I can simply tell as per G652 standard. Instead of telling core diameter, cladding diameter, nothing. All are as per it is a global standard ITUT. And these are the different types of erbium doped fiber, photosensitive fiber, bending sensitive. So different types of fiber, and the use cases may be different. Now, we are entering to so world record, that is ultra high capacity. So how this capacity recently 2 demonstrations has been done in petabits per second by NTT and also in Lucent. That is, you can see this. This is a fiber. You can see different cores within the fiber. That is the cladding. Within that cladding, there may be the different cores. Instead of a single core in the complete fiber, there can be cores. And in this core, you can see 12 crore. Okay, 12 cores, and each core is 84.5 Tbps. How it is? Each lambda carries 380 Gbps. Like that, 222, that is 2022 lambdas are there in each core. So 84.T multiplied with 12, which is equal to 1.01 petabits per second. You see, 1 petabits per second is a capacity equivalent to sending 5000 HD TV videos of 2 hours in a single second. So that is the beauty of fiber optics. Now, another world record is, this is 10.16, that is 10 times that of the previous. But here the technology is called SDM also. That is, here you can see here 19 core in a cladding. Okay. In that each core, there can be different modes. That is 6 modes. Modes means, for your understanding, I will tell, you can impinge like this. Actually, it is not right. Mode means the pattern of intensity within the fiber. For example, LP01 means sender intensity will be high. LP11 means at the 2 points against the sender will be high. So these are the different modes in fiber. You may be familiar electromagnetic modes, similar to here the polarization modes, right? And you see 19 cores, and each core is having different modes. That is 6 modes, and each mode is having 739 wavelengths, and each wavelength is having 120 gigabits. 120 gigabits, 739 wavelengths, and 6 modes, and it is you see it is 10.16 petabits per second, 10 raised to 15. That is equivalent is 25,000 Blu-ray disc, or 50 GB on both sides. So 100 GB disc of 2,500 in 1 second. So there is no limit. These are for research and others. That is actually exploring the full capacity of optical fibers by 40 Gbps onwards. It is given. If you want, you can have a look on these. Different technologies are used for this. Then the last portion is undersea fiber communication. When before the invention of the undersea fiber optics, the people used to communicate with the external or internationally by satellite communication. Now the satellite communication is used for this broadcast transmission, but point-to-point communications, internet communication, etc., 95% is now carried by the undersea fiber. That is usually India. This is the India. At Chennai, Cochin, and Mumbai are the normal landing points. And our fiber is CMIMI, that is Southeast Asia, Middle East, West Europe. And the present condition is more than 7 lakh kilometers of cable available undersea. Production is 1,50,000 kilometers per year. More than 140 cable laying ships are in the process, and 95% of the data or intercontinental communication is through the fiber. And this is to make you understand how this fiber laying is done. You can see the fiber is going. This is the fiber. You see. Okay. You see? 1 minute. You see, this is the fiber laying ship, fiber laying, and this ship first extend a code so that it will be tied. This is assume that this is the exchange. Now the fiber is coming with a float, that is to float over the Z. Now it is spliced to the nearest exchange. For example, you take the Madras point, then the floats are cut. Now the fiber will sag through the seabed. This is the seabed. Now one winch pulling, one machine will come down. This is actually drawing the fiber through the sea. Now you see the way is going. Actually, it is not under the. It is at the bottom of the sea. For example, maybe at 2,000 meters down, and the process will go on, and this will be spliced and back to the sea, the remaining portion, and this way it is done. For example, there are many players in this. For example, Flag is one company, Fiber to Link around the group, then NTT, different companies, they are making this type of contract work also. Now, if a problem comes, for example, you may be heard of that it is ruptured and internet speed may go down like that. Not working. It's not working. No problem. So, you see, if a fault occurred, then it will be taken up. Then this ship will go and will take others down up. Then it will splice and put back. So the technology is very much sophisticated. There is no question of fault more than 1 hour or 2 hours. So this is what? This is the erbium doped fiber amplifier, which is used for undersea amplification. And you can see this is the cable, and you may wonder how this fiber is amplified, etc. Because from where to get electricity, because the armors are used for, armor means the surrounding for giving the strength, armors are placed, and this will give the, one of the armors insulated can give the, this is the fiber at the center point. These are the fibers. And you see the undersea all over the globe. You can see these are the regions where America, Britain, that is, these are Atlantic region, and these are the regions where the first fiber optic communication, TAT8, transatlantic 8 was launched. At that time, it was only some Mbps range, but now it is TAT11, TAT12 upgradations happened. And this is the Indian region, Indian Ocean, and here you can see different links are coming. So undersea is now full of fibers. Okay. So to conclude, is it an evolution or a revolution? You see, from 1980 to 1990, 2000, in 2000, the bandwidth was 100 Gbps onwards. 2010, 2020, and 2040, it will be 1 exabits per second. That is EBPS. Exa means 10 raised to 18. Exa. So this is the way the world is going. And also you see, this is the, if you want to get an optical communication system, you can have this type of players available in the market. That is Rosen, Alcatel, NEC, Siemens, Alcatel. So different types of transponders are also available. Now, these are the books. Living in the City of Light is another book. Expecting a Future Full of Light, another book. Scientists are lighting the future, another book. Rise and Rise of Optical Fibers regarding the cow and all optical network. All these you can read to get a better idea on fiber optics. Now, Sandhya.
Okay.
Hello?
Is it over?
Yes, it is on.
Okay, that was a very wonderful session, Sudeep sir. I request the participants, they may raise their questions either in the chat box, or it will be convenient if you put the questions in the chat box. It is open for discussion.
Yeah.
The Google
Questions?
form for feedback is also given in the chat box. You may fill the Google form for feedback so that you may get the e-certificates. Please raise your questions.
Thank you, but the questions are welcome. C. Optical cross connect. Okay. Okay.
Okay. I think he's there.
I am here. I am hearing.
Okay. Can you please say a few words of felicitation for this program?
Oh, it is a wonderful. I just Sudeep told me, and I said I will attend. I know Sudeep because for a long time, and so I tell I will attend, and it is a good talk, very good talk. I will say
Thank you.
so much informative, and also what is in store for the future. That is a very important. If I remember correctly, in 1990, I told somebody in here that we are going to have optical communication. Nobody believed. That is in 1990. It came in the UK and other places at that time. So nobody in India believed it. And later, optical communication was introduced between Pune and Bombay. And after that, it was a revolution and everywhere. And fortunately, in Kerala, we are having fiber connection between all exchanges. BSNL exchanges, they are having fiber connection. So it is very good in Kerala, not so out in other states. They are very far off villages and etc. But here it is very good, and we are now having very good connection. Only thing is now with the online teaching etc. Sometimes the exchanges gets choked because so much data is being going through the exchanges. This is not the case in this is not the case only in India. No, it is all over the world. The last issue of Physics Today was telling it is also there in US. So just wonder, because everybody is going for online teaching. So the data communicated between the groups are very, very large, very, very large. So, but we are going along with that, and in new technologies will come and it will improve. I think nothing may replace optical communication in the future. We cannot see now. We don't know. The other electromagnetic wave parts may be used in the future thing. That will come only there. So very good. So it is a very good talk. Thank you.
Thank you, sir. Thank you, sir.
Thank you,
Actually,
Sir.
because of the Department of Optoelectronics only, I could complete my PhD and my like, for example, once after getting my job, I just saw Unnikitan sir at Vadidakad, and he told, he asked me, why can't you take PhD, or why can't you work for this? What is the topic you like that? The next day itself, I have gone to Karyavatam and I joined, and that is why I am very much dedicated to Unnikitan sir in this regard. Otherwise, I would not be at this position now. Thank you, sir, for nice advice to all the people, all the students. And Sandhya, anything?
Okay, thank you, Unikrishna. We are indeed very happy to hear your words also, because we all are your students. After a long period, we are hearing your voice. So much happy to hear, sir. Dear students, do you have any doubt in this regard? You may please raise questions. Otherwise, we will go to the concluding part. Oh, okay, sir. So I invite Srimati Sapna P, Assistant Professor, Department of Physics, MG College, Irti, to offer the vote of thanks.
Okay, thank you. Thank you, Sunday teacher. So I'm Sapna, working as Assistant Professor in Department of Physics, MG College, Kannur. So which is hosting today's session in the Professor Aruldhas Memorial Webinar Series. So I'm very privileged to be a part of this wonderful program. And I'm remembering I also got an opportunity to be a student of Aruldhas sir. So he's such a great teacher and entirely different method of teaching as I experienced. So now I would like to get into my duty. So first of all, I would like to thank our speaker of the day, Dr. VP Sudeep Kumar sir, Assistant General Manager, BSNL Kerala. So he has delivered a wonderful lecture on the topic, starting from the basic bandwidth itself. So which got a very high importance nowadays, because everything, especially our education system, has been switched over to online due to corona pandemic, as all of us know. So sometimes we may get connection, sometimes it is not. So a lot of problems with this online teaching also. So everything is depend upon this bandwidth. We have a great time over here in order to understand about the optical fiber communication system. undersea communication system, etc. So on behalf of MG College Physics Department and of course the coordinators and organizing committee of this webinar series, I would like to thank Dr. VP Sudeep Kumar for getting us such an opportunity to hear you. Thank you, sir. Thank you very much for being with us for this session. Sir, I think your microphone is muted. We're not hearing you.
Okay. I'm very much happy to be here, and also I'm very much thankful to my dear friend Sandhya, and also CB sir, Dr. CB sir, and all other dignitaries, my friends who has dropped in to hear my lectures, and my favorite and also my beloved Dr. Unnikrishna sir, and thank you and all. Thank you. Okay.
Okay, next I would like to thank the coordinators, especially Siddhika. We can see almost 160 participants are over there, but it is now 21 because, of course, that problem may be there. So, such a wonderful coordination, sir. He's also a wonderful speaker, teacher, etc. And I also have an opportunity to be a student of him also. So we also got an opportunity to host this program, that is MG College Physics Department. So on behalf of the department MG College, I express my sincere thanks to you, sir, CB sir. And of course the organizing committee, which consists of Dr. Biju, Dr. Hubbard Joe, Dr. Jayalakshmi, Dr. Jawahar, Dr. Subodh, Dr. Savida Pillai, Dr. Mamta Sahu, Dr. Jaki, Dr. Divya Krishnan, etc. So, also thanking the organizing committee. And next, today's program is convened by Srimati Sandhya, head of the Department of Physics, MG College. I thank her also, and of course all the participants. Without participants, any webinar series does not effective. So all the participants, all the faculty members present here, and especially for our program, the felicitation talk is given by Unnikrishna sir. Unnikrishna sir, I also thank on behalf of MG College Physics Department. Thank you.
Thank you.
Please all of you fill the Google form, feedback form. Only then you'll get the certificates. Okay, thank you for the wonderful session and thank you for participating on behalf of and college day. Thank you. Unikus sir, again. Conclude yelle sir. Okay. എന്നിട്ട് ഗ്യാതറിംഗ് ചെയ്യാല്ലേ? Okay.
I want to make a comment. I want to make a comment. My life as a teacher started in Kannur.
Oh.
Many of you may not know it. That is in Ensign College, Kannur. That was the only college at that time, apart from that Kasargod. Then slowly that Kuthuvaramba College also came. Talacheri was, of course, it was their oldest college.
Okay.
So when Irti was mentioned, that is also my interest. There are so many places has developed. That is in 64, 65. I was a lecturer in SN College, Kannur. After that only I went for PhD. Okay. So this is an opportunity to meet people from Kannur also.
Okay, sir.
So thank you very much. Okay, we can have the meeting.
Thank you, sir. സ്റ്റുഡൻസിന് വേണമെങ്കിൽ ഗ്രൂപ്പ് ലീവ് ചെയ്യാം. അലുമിനി ഓഫ് കാര്യവട്ടം എല്ലാവർക്കും റിമൈൻ ചെയ്യാവുന്നതാണ്. സ്റ്റുഡൻസ് മേ പ്ലീസ് take leave and thank you so much for attending this seminar. ആ ബാച്ചിൽ കുറച്ച് പേര് തന്നെ ഉണ്ട് നമുക്കിവിടെ. എല്ലാവർക്കും ഒന്ന് സംസാരിക്കാവുന്നതാണ്. നമ്മുടെ ഉണ്ണികൃഷ്ണ സാറും ഉണ്ട്, സുജിമോൾ, രേഖ, കൃഷ്ണപ്രിയ ഉണ്ടായിരുന്നു, ലീവ് ചെയ്തു എന്ന് തോന്നുന്നു. സുജി, can you please respond? And Rekha, of course.
Hello.
Hello.
Sir. Good evening, sir. സാറിന് ഓർമ്മയുണ്ടോന്ന് അറിയില്ല.
ഇല്ല, അതൊക്കെ വർഷങ്ങൾ കഴിഞ്ഞില്ലേ.
വർഷങ്ങൾ കഴിഞ്ഞു.
All of you have changed.
എന്താ സാർ? ആണ് സന്ധ്യ കൃഷ്ണപ്രിയ അവരുടെ കൂടെ ഉണ്ടായിരുന്ന.
മനസ്സിലായി. സുദീപ്.
അതെ സർ. സാറിന് എന്റെ ഹസ്ബൻഡ് അറിയായിരിക്കും, ജയശങ്കർ, യൂണിവേഴ്സിറ്റി.
എവിടെ? ഇവിടുത്തെ?
കേരള യൂണിവേഴ്സിറ്റിയിലെ പ്രസാദ്.
ഇപ്പം ഇവിടുന്ന് പോയില്ലേ?
ഇല്ല, ഞങ്ങൾ ട്രിവാൻഡ്രത്താ. ഓ,
പോയോന്ന് സംശയിച്ചാണ്.
സാർ സുഖായിരിക്കുന്ന?
സുഖായിരിക്കുന്നു.
സുജി എവിടെ ഉണ്ടായിരുന്നല്ലോ, ആ ബാച്ചിലുള്ളവരെ വിളിക്കുന്നേ. പ്രസന്റേഷൻ സമയത്ത് കുറച്ചുപേരൊക്കെ ഉണ്ടായിരുന്നു, ഇപ്പം ആള് പോയി തോന്നുന്നു. I invite the alumni to just say a few words. All alumni present here.
സുജിമോൾ.
ഹലോ.
കേൾക്കുന്നുണ്ട്.
സുജിമോൾ അല്ലേ?
ഹലോ.
കേൾക്കുന്നുണ്ട്.
ഹലോ, സന്ധ്യ കേൾക്കുന്നുണ്ടോ? ഗുഡ് ആഫ്റ്റർനൂൺ സർ. ഗുഡ് ആഫ്റ്റർനൂൺ.
Good afternoon.
ഹലോ.
Happy to see you all. കേക്കാം.
ഞാൻ സുജിയാണ്. അവിടെ
മനസ്സിലായി. പറഞ്ഞു.
അവിടെ കാര്യവട്ടത്തെ MSc ബാച്ചില്
ഉണ്ടായിരുന്നു. സുദീപിന്റെ ബാച്ചിൽ തന്നെ അല്ലേ?
ഇപ്പം അവിടെ ഇസ്രോയില് സയന്റിസ്റ്റ് ആയിട്ട് വർക്ക് ചെയ്യാണ്, ഡൽഹിയില്.
അത് ശരി.
ഞാൻ ഇവിടെ നിന്ന് അറ്റൻഡ് ചെയ്തു. സാറിനെ കണ്ടതിൽ നല്ല സന്തോഷമുണ്ട്.
അപ്പൊ ഇങ്ങനെ പറഞ്ഞതുകൊണ്ട് ഞാൻ അറ്റൻഡ് ചെയ്യാൻ തീരുമാനിച്ചത്. വളരെ സുദീപം പ്രസന്റ് ചെയ്യുന്നു, വളരെ സന്തോഷം. ആൻഡ് വേറൊരു കാര്യം കൂടെ ഉണ്ട്. ഐ തിങ്ക് സന്ധ്യ പറഞ്ഞു ഒരു കാര്യം കൂടെ ഉണ്ട്. സിബി പോയോ? സിബിയില്ലേ? സിബി പറയണം. നമ്മുടെ എന്തുകൊണ്ടാണ് ഇപ്പൊ ആലുമിനി മീറ്റൊക്കെ വയ്ക്കുന്നതിന്റെ കാര്യങ്ങൾ എന്താണെന്ന് സിബി തന്നെ പറയും.
എന്നാ ടോക്കിന്റെ സമയത്ത് വേറെ ആൾക്കാരുണ്ടായിരുന്നു. ഞാനത് ഇട്ട് കഴിഞ്ഞു സാറേ. ഇൻവൈറ്റ് ലിങ്ക് രാവിലെ തന്നെ ഞാൻ ഗ്രൂപ്പിലേക്ക് ഇട്ടിരുന്നു.
ആ
അന്നേരം
അപ്പൊ
തന്നെ
ഞങ്ങൾ ഇപ്പൊ തന്നെ ചെയ്യാം. ജോയിൻ.
ഇരിട്ടി MG കോളേജ് എന്ന് പറയുന്ന സാർ ഒരു ചെറിയൊരു കോളേജായിട്ടൊക്കെ തുടങ്ങിയാണ്. ഇപ്പോഴും വലിയ വലിയ കോളേജുകളുടെ നാലയിലൊക്കെ എത്തില്ല. എന്നാലും എനിക്ക് തോന്നുന്ന ഒരു അക്കാഡമിക് ലെവൽ നോക്കിക്കഴിഞ്ഞാൽ പ്രത്യേകിച്ചും ഈ അലുമിനി ഒത്തിരി നല്ല ഫീൽഡിൽ അലുമിനി ഉണ്ട്. കുറേ ആൾക്കാർ വെളിയിൽ റിസർച്ച് ചെയ്യുന്ന PDF ഒക്കെ ആയിട്ട് മാക്സ് പ്ലാങ്ക് ഇൻസ്റ്റിറ്റ്യൂട്ടിലൊക്കെ ഉണ്ട് 3-4 ആൾക്കാർ. അപ്പം അതുകൊണ്ട് തന്നെ അവരൊക്കെ വരുമ്പം കുട്ടികൾക്ക് നല്ല മോട്ടിവേഷനാണ്. അപ്പം നമുക്കറിയാം അതിൻ്റെ അലുമിനിയുടെ പ്രാധാന്യം നമുക്ക് നന്നായിട്ട് അറിയാം സാറേ. അപ്പം എന്തായാലും എല്ലാ സഹകരണവും ഉണ്ടാവും.
അതായത് സന്ധ്യ അവിടെ ഉണ്ടല്ലോ, ഇരുട്ടി സന്ധ്യ.
അതെ,
University 2005.
ഓക്കെ സാറേ.
ഓക്കെ,
ഓക്കെ സാറേ.
ഓക്കെ.
താങ്ക് യു, താങ്ക് യു, താങ്ക് യു.
Thank you everyone. Thanks to everyone.
എല്ലാവരെയും കണ്ടേ സന്തോഷം.
താങ്ക് യു സർ.
രേഖ, സുദീപ്, താങ്ക്
Thank
യു.
you.
താങ്ക് യു. രേഖ,
Thanks,
താങ്ക് യു.
Sudeep.
സുജി, താങ്ക് യു.
Hi, Rekha. Hi, Rekha.
ആ,
ഇങ്ങനെയെങ്കിലും കാണാൻ പറ്റിയല്ലോ.
അതെ അതെ.
അതാ അതാ.
ഓക്കെ, എന്നാ കുറച്ചുകൂടെ നേരിട്ട് കാണാം എന്നാല്. ഓക്കെ
താങ്ക് യു,
ആ നമുക്ക് സൂം മീറ്റിംഗ് എടുക്കാം.
ഓക്കെ
താങ്ക് യു.
ഓക്കെ താങ്ക് യു.
ഓക്കെ.
Okay, bye.
താങ്ക് യു സർ, താങ്ക് യു, താങ്ക് യു.
ആ സുദീപ് പോയാ.
ഓക്കെ.
എല്ലാരും